this video I look at one practical problem solving technique, that's of finding general solutions by solving specific instances. This is a practical one. Specific instances. Now I do not recommend this as a go-to technique for solving problems because it is not a theoretically very sound technique. As opposed to the theoretical approach, the technique that you use by using a formal approach is far more greater, it offers a better scope. But nevertheless, this is also very, very effective. That's why I'm mentioning it, or it is worthy of that. Here what you do is you just take a particular specific problem and solve it. For instance, for hashing, you take one particular number and try to hash it, ensuring that the order is preserved. So here I will illustrate it as follows. So I'll give you a couple of examples where this works. There's a third one where it's very, very effective. In fact, perpetual hashing also can be solved this way, but I'll not go into that. But I'll take two simple examples. Here I wish to perform an ordered hash of a 6-digit number. Here, the example that I'm taking is this. It is 573862. So this is a number that I've taken. This is a 6-digit number which I wish to reduce to a 3-digit number, that is a value between 1000 to 1000 different values. So since this is a 6-digit number, therefore I take r power 6 equal to 10 cube. So r will be equal to 10 power 3 by 6 equal to 10 power 1 by 2. Okay. Here, because it is exactly half, what happens is the unit increment will be root 10 now. Okay. And since it is exactly half, the multiplication factor will also be root 10. So essentially the hash essentially becomes here is because we are directly taking it this way, it will also fairly preserve the distribution of numbers itself. It will mimic that fairly because we are using powers here, directly doing it. So it will be 5 into 1 by root 10. The hash will simply become 5 into 1 by root 10 into root 10 power 5 plus 7 into 1 by root 10 times root 10 power 4 plus 3 into 1 by root 10 times root 10 power 3 plus 2 into 1 by root 10 times plus 3 plus 8 into 1 by root 10 times root 10 square plus 6 into 1 by root 10 times root 10 plus 2 into 1 by can calculate this value comes up to approximately 783.2901113. So you can just take this value. Since this is, you can round it up. If it is more than half here or something, you can make it one more. Okay. So this value will be the hash value. From this, we can generalize as follows. We can completely generalize it. So if b power l dash is mapped to b power l, a number in the base b, where l dash is equal to l into c. C is a constant, fairly, need not be too large and need not be too small. Then we find r equal to b power l by l dash equal to b power 1 by c. And the unit again will be u is equal to b power 1 by c by b equal to 1 by b power c minus 1 by c. And the hash value will simply be summation bi b power I is mapped to summation di u times r power I. So this will be the generalized, because now we have solved it for a specific instance, therefore we can generalize it, finding the solution for specific instances. Another example of this is with the same thing, is with the same number I should take another way of hashing it. This one is usually now again we wish to hash a 6-digit number to a 3-digit number, which is 1000. But I shall take the binary approach here and make it 1024, which is the closest binary value, slightly larger than 1000. So I'll hash it to a value up to 1024. So you simply proceed as follows. You write this as 5 having done this. Okay. So this will add up to your key value. And on this side, I will start off with here, the largest one I would require 1024. And then this one I would require 512. This one I would require 256. This one I would require 128. And this one I would require 64. Okay, now this means here these last two digits, there are 100 possible values, but here I require only 64 of them. So simple arithmetic you can do, proportional arithmetic itself. So the value will be 62 into 64 divided by 100, which rounded up comes up to 40. Okay. Now for each of these 40 possible values, so maximum here, this would have been fairly order preserving, but here again we need to make it order preserving and to hash to a value up to 128. But there are only 10 possible values here and a maximum of 64 values here. Okay, so the hash value will now become so the maximum possible hash value will be 64 into 10. Right? So what we do is we simply multiply 8 into 64 plus 40 here maximum value will be 640 into 128. This will come up to the hash value 110. So we start off now again 110 up to 128 and 10 possible values for the previous this thing. So 1280 will be the divisor, and multiplication will be, again scaling factor will be 256 now. So this will be 3 into 128 plus 110 by 1280 times 256, that will be equal to 97. After rounding it up or down, it comes to around 97. Now again we repeat the same thing, but now with 512. So we will again, this will be 7 into 256 plus 97 whole divided by 2560 into 512. This will come up to the value 377. Finally again we have 5 here, so you will have 5 into 512 plus 377 whole divided by 5120 times 1024. This will come up to a value 587. So this will be the hash value for it. So here also you can generalize it. This basically is a way, one way of just doing it binarily. You have fix a base and do it binarily. So each time you reduce till you bring it down to a fairly small amount where the ratio of binary to the base of the key is not too much, then the probability of a collision will be very, very small, almost negligible. And in all these techniques, you must remember that since you can always take use of the fact that you can split the size of the S or the hash value over specific ranges in different based on that where they appear. So you can apply this technique for different keys over different ranges. So you can make slight improvements to all of these designs. Here again you can make it, now having discovered this technique, we can try and normalize it or make it, generalize it as follows. The simplest one will be b power L dash to 2 power L dash minus some small quantity A. A can be very small, 2 or 3 or something like that. Like we saw, that is the simplest one. We can also go the other way. We can also map in general b power L dash to b power L, where L dash by L is equal to C, and like we just did there, we map b power L dash minus 1 times b power L dash minus 1 here. Then this will be equal to 2 power L log to the base 2 b. You have 2 power L be d L dash minus 2 b power L dash minus 2 to 2 power, minus 1 or 2 power L, 2 power L log b minus 1 and so on up to d power L dash minus x plus 1 b power L dash minus x plus 1 into 2 power a, where x equal to L times log b minus a. So we can proceed by in this fashion also, or we can directly do it simply from 2 up to b power L dash to 2 power L dash minus a. Either of these approaches we can adopt. Now, while this is a simple practical problem solving technique, it is very effective. That is why I made a small video of it, but this should not be the go-to of, I have not written the main stable approach to solving problems.